Please turn your manuals to page 23. Installing the Hydro Assist fuel cell. That is the wiring diagram that we're using. This relay is a 5-prong relay. Pins 86 and 85 activate the relay. Pin 30 and 87 are what the relay activates. So pin 86 gets grounded. Pin 85 gets hooked to your switch. The switch is powered by the fuel pump relay. The fuel pump relay is used because if you turn the key to the on position and do not start, that relay will activate for 2 or 3 seconds and then shut off. So if someone were to get into the vehicle, turn the key on, and not start it, we're not sitting there filling the engine compartment full of water gas. If they try to crank it and it doesn't start and they let off the key, again, the fuel pump relay will turn off. We're not filling the engine compartment full of water gas. We want water gas only when the engine's running, right? So an easy way to do it is we get water gas only when the fuel pump relay is activated. Everyone follow the logic on that? That is the only thing we're tapping into the fuel pump relay for. I've had people who have gone through the class, unbeknownst to us, because we don't exactly stand right over your shoulder while you're doing everything, but we had people trying to hook up the power feed for the optimizer off the fuel pump relay. Had a neon, just couldn't start it. Could not start it because it wasn't getting any power. The optimizer wasn't powered. I mean, they turned the key on and, you know. Anyways, there is a fuse, comes in the kit. See here, we should have our components back here somewhere, right? Okay, relay. Yeah, relay, got relay. Switch. Yeah, got a switch. Hey, fuse. Wrong relay. So this is the inline fuse holder. And that goes between the battery and either the red or the yellow wire. Doesn't matter whether you go 30 or 87. It's just a continuous path. That'd be the red and the yellow wire on this connector. So you put the fuse here, and then the other one goes to here. This one then goes to the battery. Got it? End of the fuse goes to the battery. The other end goes to either the yellow or the red wire. And then the other yellow or red wire, whichever you didn't use, gets hooked up to the red wire on the fuel cell.
I can't see your fuel cell. Just move it to the right or the left.
See? Then the black and the white wires. Black wire, you can loop back around assuming that the relay gets mounted up against the fender or somewhere that it contacts chassis ground. You just put an eyelet on there, and then the mounting screw to hold the relay in place is also your ground for that side. Then we come out of the other side. This gets plugged into the center prong on the switch. The plus prong on the switch goes to the fuel pump relay output. In other words, whatever powers the fuel pump. So when the fuel pump relay is putting out to the fuel pump, you're getting power to this switch. And then from this end, fuel pump relay, center goes to your fuel cell relay. And then if you want this to be an illuminating switch where when it's on, it's lit up, then this third prong, which is listed ground, you just simply run to ground. And then with that grounded, whenever the switch is turned on, the current going through the switch will light up a little LED inside, and it'll be an illuminated switch. So that third is optional. You don't have to hook it up for the switch to work. It just makes it a lighted switch. Any question on the wiring? Pretty simple. Whoever did this book did a good job on that drawing. Actually, I didn't do this drawing.
Oh, no.
Someone else did this drawing. Okay, there's a couple pictures in here. The fuel cell you want mounted level. You don't want it sitting on its side. You want it mounted level. You want it mounted securely. Don't just bungee strap it in somewhere. Securely. You can drill holes, as we had discussed, to mount brackets. You can weld brackets onto the dry side. You can make a little cradle, sit it in there, and then put metal straps around it. Secure and level. Everybody understand that? The dryer will go preferably someplace a little bit higher. And this one, this is where the inlet is. And this is where the outlet is. This also should be mounted fairly upright. This is tilted a little bit, tilt it this way more so than this way. Definitely don't tilt it this way. Now you got to make brackets for this stuff, or straps, or something that's not included in the kit. So, you know, a hose clamp around something, whatever you decide, just make sure it's secure. When you mount these, make sure you can get access to fill it up. Make sure you can see the sight glass when it's mounted. Those are two very key points. You got to be able to see if it needs any additional water, and you got to be able to put it in when it does. And since this, in this current configuration, will periodically need emptying, again, you want access to the top port because there's a little squeegee that comes with it. And what you do is when you can see you're starting to build up liquid, take the squeegee, stick it down in the bottom, suck the liquid out, pour it right back in the fuel cell. Recycle it. So you want to have visibility and accessibility. Are there any questions on the physical mounting of these two components? Okay. We're going to come off the top of the fuel cell and go into this port. The one that was listed on the board, you had a high port and a low port. You want to go from here into the lower port. And then from the higher port, you go into the air filter housing. Preferably so that the gases have to go through the paper filter element before going into the throttle body. I would mount it as low as possible. Where they have that mounted is kind of like in the middle. But what we're finding is if you mount it down lower, if you do get any liquids, it's a bigger jump to hit the paper filter element. And we've had some extreme cases where there was excessive foaming and bubbling, and it would actually get into the throttle body right through the paper filter. So the lower you can mount that, the less likely it will jump and get in the engine. Any questions on that? The hose is included. Pass this around. In the kit. It's basically this polyurethane reinforced plastic, or fiberglass reinforced plastic. I don't know, it's got some kind of a cloth reinforcement in there.
What would happen if someone has those K&N filters on this, you know, where they're just open?
It's treated just like any other air filter as far as the installation goes.
Yeah, but he means there's no box to put the hose in the bottom of. It's just an open filter.
Oh, the cone filter.
Yeah.
Yeah, the cone filter. You have to get creative. You can knock a hole in the side, and you know, you get one of these in the kit. So yeah, if you can just 1/8 NPT somewhere, screw this in. That's what this is, 1/8 NPT thread. So just, you know, drill, I think it's an R drill bit size, and tap it out and screw it in there somewhere. I would put it on the bottom side of the hose, if nothing else.
Wouldn't it be going through the filter then?
Nope, you're right.
Gotta risk it. It's not your problem they put it on there.
How about in same cars, in like racing cars, in just a pipe, aluminum pipe, and a filter? Outside, not boxing.
That's basically what he just asked. Just you're going to have to make it up as you go. I'm hoping that you will understand the system well enough that when you do run into oddball stuff like that, you can kind of fill in the blanks that we may have not covered here.
What about an inline filter in that hose, like those old, like,
Fuel filters like a G12 frame or something,
Glass one or something you can see.
probably wouldn't hurt.
How much pressure have when it pumps the
It's 60 liters per hour. If there's any pressure, it's because you got a kink in the hose somewhere. Shouldn't be any pressure, not any measurable pressure.
Can you just explain to me?
more or less is whatever sucks
in other words, you're saying you have to put a switch to the relay?
Yes, the switch is like a serviceability. Did I put it back over here? If I wanted to shut this off, I could do this. Or I could do this. You want to put this in as a safety device or as a serviceability device. Is this switch absolutely necessary for the thing to function? No.
Okay.
But we add this in here as just an extra protection measure. Just like the fuse, you absolutely need the fuse in there only if you have a problem. You need this in here only if you have a problem.
and then the lights actually tell you something's happening.
Yeah, I mean, at least you get
When
the
the
light to
lights,
it's on.
when you hook up the
Well, lights sell. You know, it's like on my Spirit, I made up a custom strut tower bar. And instead of drilling holes in my one of 1,206 Spirit RTs to mount this switch, I actually drilled holes on the bottom of this custom strut tower bar, which I can remove and not alter the vehicle, and that's where it's mounted. So you pop the hood, and over on the driver's side, next to the upper strut mount, is this little bracket hanging off the strut tower bar. Nope, I didn't even drill holes in my car. Well, yes, I did, but not to mount the switch. I'm telling you, I believe in this. For me to drill holes in my one of 1,206 Spirit RTs, you know I believe in this system. All right. There's several pictures of components mounted. You'll see on page 26 that amp gauge that I told you about. Just kind of clips around the wire, and then you can monitor the DC amps being drawn by the fuel cell. On page 28, there's a shot of the vaporizer mounted between two radiator hoses, or heater hoses, excuse me. And another trick that we use is we take aluminum foil and wrap it around the whole setup to help retain heat and to convect the heat to, the back side of it. And someone has suggested that there's this, it's like half-inch thick bubble wrap with foil on both sides. It's used as insulation. You can purchase it from Home Depot. It's supposed to be real cheap, and that will actually do even better than just wrapping aluminum foil around it, because you have an air gap that will double insulate it and hold more heat in. So anything you do to add heat, within the realms of coolant temperature, the better. Page 29, we're showing the optimizer getting wired up right at the ECM. Page 32. Older vehicles, whether it's a 1-wire, 2-wire, 3-wire, or 4-wire oxygen sensor, only one of those wires is used in signal. You only have one signal wire. The oxygen sensor itself is kind of like a battery. It generates its own voltage. It's not like a MAP sensor or TPS where voltage is fed to it and it has resistance. It generates its own voltage. You have two rare earth metals in there that when you heat them to 660 degrees Fahrenheit, will produce voltage in the absence of oxygen. Gosh, that was a mouthful. Let's slow down, back up, and break that down. If there's no oxygen, okay? High oxygen level, no voltage. As the oxygen levels drop, the voltage level goes up. So if you have a lean mixture, you have a high oxygen content, right? If you have a lean mixture, high oxygen content, you're going to have low voltage. As the mixture richens up, the oxygen content goes down and the voltage goes up. Everyone follow that? The typical range for the older oxygen sensors is deemed 0 to 1 volt DC. In practical application, I played around with one with a torch, and I got like about 2.2 volts out of one, because in the flame front of the torch there was no oxygen. I got plenty hot, and I'm watching on a voltmeter cool. As I move the torch away, I can see the voltage. Anyway, 0 to 1 volt. So the ECM is looking at a midpoint as 14.7 to 1. That midpoint equates to be about 0.53 to 0.55 volts. All right? Everyone follow that?
So this is behind the catalytic converter or before?
This is before. Behind the catalytic converter has nothing to do with how the engine runs. All it does is say, yes, computer, the catalytic converter is working. That's all that thing is
Actually,
worth.
The difference is important. Between both of them is the difference important.
Yeah.
If it don't fluctuate,
We do nothing with the downstream sensor.
upstream sensors,
So we're not even going to mess with that post-cat sensor. That downstream sensor, we're not going to do anything with it. Guys recognize that? That'd be 15, yeah. Yeah. So when you go lean, the voltage drops. When you go rich, the voltage goes up. The effective range is 15.1 to 14.3, where it's targeting 14.7. 14.7, again, you're looking at about 0.55 volts. At 15.1, you are looking at about 0.40 volts. No, 20 volts. 0.20 volts. 2.5. I have to think about this. At 14.3, it's about 0.75 volts, I think. Now, the computer sees this, and anything leaner than 14.7, any voltage less than 0.55, the computer's analog to digital converter says binary 0. Anything richer than 14.7 to 1, any voltage greater than about 0.55 volts, the computer's analog to digital converter says binary 1. These systems see binary 0, binary 1. Lean, rich. Lean, rich. So if we wanted to remove excess fuel, because we're going to vaporize more of it. In fact, I got to get off on a tangent here. 1950 Oldsmobile, right? Flathead 6, 1-barrel carburetor, choke on the dash. Everyone has been telling us 14.7 to 1. That's where it's at. Let's take a look at this 1950 Oldsmobile. You go out tomorrow morning and you try to start that Oldsmobile. Until you pull that choke lever out, it ain't going to start, is it? Yet with that choke lever out, are we at 14.7 to 1 air-fuel ratio? We're about 3 to 1, aren't we? So we get it started, and then we can push it in just a little bit, maybe take it up to 6 to 1. And after 15 seconds, now maybe we're up to 8 or 9 to 1. After a full minute, we might be at 12 to 1. So 14.7 to 1 doesn't work when it's cold, does it? So What is 14.7 to 1? That's 14.7 pounds of air for every 1 pound of fuel, right? 14.7 pounds of air to 1 pound of fuel. That's air and liquid fuel. But if it takes 3 pounds of air to 1 pound of fuel to start that old 50 Oldsmobile, then why? Because the engine's cold? It's not vaporizing any fuel, and liquid fuel doesn't burn, right? So we need to just literally pour it down the engine to just get that little tiny bit of vapor just to get that engine started, right? Once we get the engine started, then we start creating a little bit of heat inside on the valves and the combustion chamber and the piston surface. Now it starts to vaporize a little bit more fuel, so now we can go from 3 to 1 to 6 to 1, and then 12 to 1. It's probably safe to say that the engine couldn't care less about a 14.7 pounds of air to 1 pound of fuel ratio. It's actually looking for a number of oxygen molecules to fuel vapor ratio. Right? Yeah. Because if you're running in the winter, I don't know how meticulous some of you older guys were with your cars back when everything was carbureted, but you could actually run winter jets and summer jets. You put smaller jets in the summer because there was fewer oxygen molecules in the air, and you'd save fuel if you leaned it out in the summer. Then it didn't want to run right in the winter, so you had to put the bigger jets back in. So it couldn't care less about pounds of air and pounds of fuel then, could it? Heck no. It wants to see a certain number of oxygen molecules for a certain number of vaporized fuel molecules. That's all it wants to see. So then if we're going in and we're heating the fuel, then we can turn the choke off a little more, huh? And if we're putting some water gas in there that's going to help that OC radical process and just go in there and rip and tear at those fuel molecules, chances are we don't need as many of those fuel molecules, then do we? And we're putting chemical stuff in to, again, help vaporize the fuel even more. Let's turn the choke off some. How about? We can lean this out from 14.7 pounds of air to 1 pound of fuel to less liquid fuel and keep the same amount of fuel vapor that the engine needs, right? I mean, doing all these other tricks, the engine's still going to see the same vapor that it needs, right? With less liquid fuel. Okay, so we're going to create our own little analog to digital converter. And on page 32 is how that analog to digital converter plays out. The 3X optimizers are shipped with an analog to digital converter that creates a binary 1 not at 0.55 volts, but at 0.16 volts. So anything over 0.16 volts coming from the oxygen sensor, the optimizer sends to the ECU a binary 1. A 3/4 volt signal. And anytime the oxygen sensor voltage drops below that 0.16 volts, the optimizer sends the computer a binary 0, approximately 0.35 volts. Before I go any further, do you understand what I just said? If you don't, please raise your hand. Help me to cover it better. Because if you don't understand this, the rest ain't going to make any sense either. Do you all understand what I just said?
I have a question.
Yes.
I don't know if I have this right or wrong. The digital signal, when it runs rich, it's giving us about 1 volt. You're saying the digital signal is 1 in a normal vehicle.
In a normal vehicle, the digital 1 occurs anytime the O2 sensor voltage exceeds 0.55 volts.
Okay.
So if we have 0.56 volts coming from the oxygen sensor, the computer extrapolates that as a rich mixture, a binary 1. If we have 0.54 volts coming from the oxygen sensor, the computer sees that as a lean mixture, a binary 0. Now that 0.55 is a little bit different from vehicle to vehicle. That's just the most common number. Some of them are 0.50, some are actually like 0.48.
We're changing it to what, 0.16 and 0.35?
Yep, so our low signal is going to be 0.35 volts. Our high signal will be 3/4 of a volt, 0.75. What's going to toggle that? Wherever we set our optimizer, it's set from the factory at 0.16 volts. 0.16 volts is probably spot on for that Escort. All right, small 4-cylinder. We're going to add 60 liters per hour of our water gas, add a little bit of thermal energy to the fuel, 0.16 should be about right. That Toyota Land Cruiser is probably going to want to see at least a 1/4 volt trip point. Now, again here, we're going to, I like a 15.1 air-fuel ratio, whereas the Ford Escort, it might be happy at a 16.5 to 1 air-fuel ratio. We're taking the analog to digital conversion, putting it into the optimizer, not the factory ECM on these. So if we want a richer mixture, then we turn up that trip point. 0.16, we're getting stall-out conditions. The thing won't idle. Then we turn that 0.16 up to 0.2, to 0.25, to 0.30, to 0.40, whatever it takes to get our drivability back. So we're richening the mixture as we turn the optimizer's trip point up. We want to lean it out, 0.16, 0.15, 0.14, 0.13, we can lean it out. Does everybody follow that? I know it's going to be real easy to lose you. Please, if you have any questions, I'm going to stop frequently in this segment because this is important that you get this. Yes, sir.
Okay, so your beginning point would be, like you had the 0.25 volts or the 0.55 volts, or that's basically where you're starting to adjust it. Is that what you're saying?
Well, it's shipped at 0.16.
0.16 is.
But what's happening is, with the factory system, with the factory ECU controlling things, you're actually going to sit there, and if you were to watch like a scope or an analog voltmeter, which you have to use digital because it's high impedance, but you'd actually see the oxygen sensor signal bouncing up and down, up and down, up and down, as many as 22 times a second. Rich lean, rich lean, rich lean, rich lean, just bouncing, 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 but it's hovering around this 1/2 volt arena. So when it's saying rich, it's because it's gone above 1/2 volt. When it says lean, it's because it's gone below 1/2 volt. And so it's like a servo circuit. It's a target. The computer's targeting 1/2 volt. Whenever it gets a little richer than that, it goes to enleanment mode. Whenever it goes leaner than that, it goes to enrichment mode. It just keeps going rich lean, rich lean, rich lean, back and forth, toggling there. And what we're going to do is we're going to, instead of toggling it here, we're going to lean it out and toggle it down here.
So we're gonna start at 0.16.
This is how we're pulling the extra fuel out that we no longer need. All right? So, we're heating the fuel. We're throwing some water gas in there. Now we got way too much fuel. You just bolt these components on, guess what? You're lucky if you get a 5 or 10% increase in fuel economy. Because the computer's fighting you.
Because the computer would compensate.
If all we did was attack the oxygen sensor, we wouldn't get very far. But that is the heart of getting our mileage gains, is that oxygen sensor. Because when we're cruising along, the computer is just trying to target whatever that oxygen sensor tells it. And if we let the factory system prevail, doesn't matter what we do to the car. Guess what? It's going to use 14.7 pounds of air for every pound of fuel, period. We ain't going to get any mileage gains with the... I mean, you can bolt 5 of these things on that Escort out there. Guess how much fuel economy you're going to gain? A little bit, but not a whole lot.
Okay. Next question. What about on older cars when some of them, the oxygen sensor never change? In all fairness, from my experience having a shop, people don't change their oxygen more or less.
That's your job to sell that. If a vehicle comes in and it's got 130,000 miles on it, it's 22 years old,
And
why don't you sell them an oxygen sensor while it's in?
I just wanted to make sure.
In fact, why don't you take a look at the ignition wires and see if maybe they're not shorting off at the valve cover or exhaust manifold, worse yet. And if it needs spark plugs, distributor cap and rotor, if it has a clogged catalytic converter,
Yeah, I have to.
that's your job to make sure the vehicle's operating properly before you send it out. If it has exhaust leaks at the manifold, what's going to happen to your oxygen sensor signal? So you got to make sure that the vehicle's functioning properly, as part of doing this.
I missed something. All right, you said we're gonna go to the 0.16 volts for our new switching point.
That's the way it's shipped, but that may not be what you want.
Right, what is this about then?
All right, the top graph is a simulated oxygen sensor signal. It is analog. The bottom is our optimizer output. When the oxygen sensor says this, the optimizer says that. And if you take the vertical lines and line them up, you can see that when you have 0 volts coming out of the oxygen sensor, it's probably because you just fired the thing up, the oxygen sensor is cold, and it's not putting anything out. So in those conditions, the optimizer puts out 0 volts also.
So it's going between the O2 sensor and the PCM.
You're going to cut the oxygen sensor wire entirely. You got 2 wires coming off the optimizer. 1 wire goes to the oxygen sensor, 1 wire goes to the computer. So we're going to cut the oxygen sensor wire interface in between. The oxygen sensor no longer talks to the vehicle's computer, it now talks to us. And we tell the computer what we want it to hear. Thanks for bringing that up. So the oxygen sensor says 0 volts. The optimizer says 0 volts.
So actually, you're talking about a rheostat on there that we can actually tune the switching values with this rheostat on the optimizer itself. Which is a series connection to the PCM.
Here's your adjustment on the early optimizers. There's a little pocket screwdriver hole there, a little slot. That's how you're going to adjust the oxygen sensor switch point on these.
Tell you which direction does what?
Let's all say a prayer that tomorrow we get a functioning, working, not just a, hey, look at this, guys, but one that actually works, ammo box with a new optimizer that has been calibrated to work with this. That's the goal of this class, is that we're going to have at least 1 ammo box and 3 optimizers that will interface with it. So essentially we got lean is 0.35 volts, rich is 0.75 volts. What's lean and what's rich? Well, we determine that by turning the screw. So that switch point as shipped is 0.16 volts. Some vehicles like to see it richer than that. Very, very, very few like to see it leaner. Let me point out why. If we go from 3/4 of a volt to 1/4 of a volt, we've gone from 14.3 to 15 to 1 air-fuel ratio. But look what happens to the voltage after that. You go from 15.1 to 1 air-fuel ratio at 1/4 of a volt to 18 to 1 air-fuel ratio at about 0.15 volts. You got a little bit of a change in air-fuel ratio here, and you have a big change in voltage. But once you get past that threshold, then a big change in air-fuel ratio means a small change in voltage. So if you're going to start out, if you go in and you check the optimizer, which I'll show you how to do tomorrow, you check the optimizer and you crank it up to 0.4 volts. That's where you're going to switch. Instead of 0.16, you're going to crank it up to 0.4 volts. Toyota Land Cruiser, be a good place to start. All right? And then you take it out and you start driving. Well, you can turn that a full turn. Okay, how do we do? How do we do? Maybe turn it 3/4 of a turn. How do we do? How do we do? But after you start getting down around 0.16, just a little twit of that screw is going to make a big difference in air-fuel ratio. It's only a small change in voltage here, but this is where we're at. That small change in voltage clear out here is a big change in air-fuel ratio. So when you start getting it really leaned out, just a little 1/8 of a turn, maybe a 1/16 of a turn, just a little twitch, and you've gone from just about perfect to way, 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 way lean. And then when you back it off just a twitch, you've just added a whole lot of fuel to it. Whereas when you're around this area, I mean, you can crank that voltage and crank that voltage and crank that voltage, and it has very little effect on the actual air-fuel ratio. Do you all understand that concept? Because of how these work. This is important when you're tuning. The switch point, right. Right here, the 0.160 volts. So as the oxygen sensor voltage comes up, at this point, we're putting out a lean signal. As soon as the oxygen sensor voltage goes above our trip point, then the optimizer puts out a rich signal. Now, it is hypothesized that under wide open throttle, the ECM is going to look for a pig-rich mixture coming from the oxygen sensor. It's no longer binary 1, binary 0 crap. It wants to see close to a volt. And so whenever the oxygen sensor voltage goes above 0.9, the optimizer will put out 0.95 volts. We've gone above and beyond just a rich signal, the 0.75 volts. We're going to crank it up to 0.95 volts. Because some vehicles are going to want to see that rich of a mixture. And if you're accelerating where you're out of open loop, the parameters are changing so rapidly the computer can no longer rely on an oxygen sensor signal. It pops into open loop. And if you're accelerating in open loop, the computer may want to see, a very, very high voltage because it doesn't want to go into detonation. It doesn't. The factories don't like buying engines. And so they would rather waste copious amounts of fuel, dirty up your oil, clog your rings and your valves under wide open throttle than to replace an engine because you knocked a hole in the piston because it was too lean. So whenever we go pig-rich on the actual oxygen sensor, we're going to go pig-rich on the optimizer too, so that it doesn't just keep dumping more and more and more and more and more fuel under wide open throttle trying to get that voltage up. We're going to, tomorrow, have an optimizer up here. We're going to look at the voltages. And we're going to look at a few other things. This will become a little clearer when you can see it happening. We have this little gizmo. This will be our oxygen sensor. All right? This will give us a 0 to 1 volt signal out of these two wires. So this will feed our optimizer. I had it laying right here, I thought. Oh, you guys are passing it. That's fine, that's fine. Yeah. We're going to actually feed this signal into the optimizer as an oxygen sensor signal. So as we increase the voltage coming out of here, we can watch what the optimizer does with it. It'll become a little clearer. So the oxygen sensor is one area that we're going to address. Now, there's parameters. We all have 5 senses. Some of them a little sharper than others, but we have touch, taste, smell, sight, and sound. Did you guys hear that? On the back of your neck, so it was a slight pressure pulse that corresponded with that closing of the door. So your sensory nerves picked up a feeling of that pressure pulse while your ears picked up the sound. And it's possible, depending on the time of day, there could have been a slight, light and then darkening effect as the sun shone through the open door and then stopped shining. You see it? The door's open. Can you see it bouncing off the walls? And you heard that and you felt that pressure ever so slightly, just subtly. Now, if your senses don't agree, that's when you panic. If you felt that pressure pulse, as subtle as it was, and you didn't have a noise or something to correspond with it, a little yellow flag would go off. The computers are the same way. We can lean out the oxygen sensor so far before it starts saying, wait a minute. The temperature of the air coming in here is this. The engine's at that temperature. My TPS says I got this throttle angle. The map sensor says that I got this much load. Mass airflow sensor says I'm consuming this much air. How in the Hades can I still be rich? That oxygen sensor don't know what it's talking about. I got to go see a doctor, man. I'm losing my mind. In the meantime, it ignores the oxygen sensor. So now we need to start telling the computer a whole bunch of lies, because when you lie, you better be good at it. You better get all your stories straight, because you screw up once, and that's it. Everybody knows you for what you are, a worthless, filthy liar. And we're going to be that worthless, filthy liar to the computer. So we got to get our stories straight. We can't let the computer actually know how cold the air is coming in. We got to tell it it's hotter. The engine's got to be hotter. The load has to be lighter. Whatever we got to do to make that oxygen sensor signal believable. We got to get our cronies in on the lie. We got to get these other sensors lying for us too. I am going directly to the 4x, and then we're going to dissect what's in the 3x from there. Just so you know, this is the same thing that I sent to the electronics engineer. Now, me and the electronics engineer had long discussions ahead of time, so this is a summary to him, a refresher to just reiterate everything that will be going into the 4x optimizer. Now let's look at number 1, keep alive memory. One of the issues that was noticed early on in development was you bolt the kit on and a 1x or a 2x optimizer, and you took the car out and you were getting double the mileage first tank. Second tank, it dropped down to maybe 50-55%. By about the fourth tank, most of the mileage improvements just kind of fizzled away. The computer started catching on and compensating and just wreaking havoc. The proper fix is to go back and retune, and go back and retune. A good piano tuner will come out and sit down with your Steinway, and he will tune it. And then as he's leaving, he'll say, I'll see you again in about a month or two. And he'll come back in a month or two and he will retune it again. He will do this every couple of months for about a year, because brand new strings will stretch easily. Then you got to crank the tighten them back up to bring them back into the proper pitch. And then they'll go out of tune not quite as easily as they did the first time, but then you got to crank them up again. And eventually, those strings pretty well stay. Well, that's the same thing with the computer, the adaptive memory. If you just go in there and tune it, you just stretch the string, but then the adaptive memory is going to come back and start catching on and working ways around you. Well, you go back and you tune again. And pretty soon, after about the third tune, the strings stick and your mileage improvements stay. We're trying to design this so that you guys can do the install, do the tune, swat it on the rear bumper, see you later. So what we've designed is keep alive memory disrupt. That means every time you start the engine, you just wiped all the short-term memory out. Yes, sir?
What are you doing on like what are you doing on a GM car, like a 3.1 or a 2.8 that's got an auto-learn process, and every time you unhook the battery, you got to teach it idle, otherwise it stalls and stops.
Yeah, some vehicles you don't want to do this. Subarus are like that, if not worse. Okay, what he asked was, how about vehicles that when you disconnect the keep alive memory, they're your worst nightmare for the first 2 or 3 minutes when you start it up? GMs, Subarus, a lot of the newer cars. Well, then you bypass it. There's a little switch on here. It says IM test and normal. The reason it says IM test and normal is because for all intents and purposes, you're going to be able to cut the keep alive memory going to the ECM. If you're looking at an all data Mitchell or factory service manual, you'll have one, sometimes 2 wires. That the only thing between the ECM and the battery is possibly a fuse. That wire does not go through any switches. That wire does not go through any relays. That wire does not go through anything with the possible exception of a fuse. That's your keep alive memory. So we go in and we cut that wire, and then we run it through the optimizer. So every time you turn the key off, it's like you just pulled a battery cable off, except you don't have to reset radio stations and security alarms. All you're disconnecting is the ECM's keep alive memory. Turn the key on, reconnects it, computer works just fine, but it doesn't get around your tuning. Vehicles that are murder, you can just turn this to IM test and leave it that way. If it's a vehicle you know right up front, there's no way it's going to work, don't even hook up the 2 wires. Don't cut the keep alive memory, just skip that part altogether. Now, it's better to not use that keep alive memory. Tune it. Drive it for a week or 2. Tune it. Drive it for a week or 3. Tune it. Drive it for a month or 2 and tune it. Because you're going to get long-term memory mileage gains. The keep alive memory now becomes your friend. So for your personal vehicle, don't do the keep alive memory thing, because you're going to be driving it every day. You can take the time to go back and tune and retune and retune. But for your customers, you just put that little keep alive memory disrupt in there, you get her tuned, and you just kind of eliminate the short-term memory fighting you. But I'm still going to recommend that you try to make like a 2-month down the road appointment with your customers. Make sure that they're maintaining properly, that they're only adding, distilled water, and they didn't knock something loose or forgetting about it, and then go back and retune it while you got it in. It takes 10 minutes at the most. So first thing is keep alive memory. It disconnects the keep alive memory from the ECU when the key is off. Uses 2 wires of the same color on the 4X. The 3X uses a gray wire and a white wire, and it's not polarity sensitive. Then has this bypass switch labeled IM test and normal, whereas IM test keeps it hooked up all the time. It bypasses the board mount relay. When you put it on normal, then whenever you turn the key off, the relay will disconnect the keep alive memory. Any questions on the keep alive memory circuit? Number 2, 2 coolant temp sensor offsets. All right, coolant temp sensor, most vehicles have 1. That's all you got to deal with. Most vehicles that do have 2 or 3, one's for the cooling fan, it's more of a thermal switch, one's for the gauge, but you usually only have 1 that they have to deal with. Now Dennis's Honda out here happens to have a second one in the radiator. It does nothing more than control the cooling fan in theory. But if that sensor and the one in the cylinder head that we want to get to and that's going to be our friend, if they don't agree within a certain range, then it trips codes. So we had to incorporate not 1 but 2 coolant sensor circuits, 1 to address the one in the head and 1 to address the one in the radiator. The one in the head's the only one that's going to help us out, but the other one just keeps us from tripping codes. So on the 3X optimizer, we have a sensor. That's the black helicopter around the building here. Don't worry about it. Now, no matter whether it's 3X, 4X, 1X, 2X, you got a ground wire coming off the optimizer. Black wire. Red wire is key on and crank. Not just key on, but key on and crank. Especially if you have the keep alive memory wire hooked up, because if you don't have crank also, then you don't have keep alive memory. We had a neon, we could not get started. We had to go back and meticulously start retracing all the wiring, and it turned out that someone found a nice convenient wire that was just key on but not crank, and so in crank we had no keep alive memory and the computer didn't function, we couldn't get it started. So it's got to be key on and crank. And then the way the 3X is wired, we're going to go in and we're going to not cut, but splice into the signal wire side of the coolant temp sensor and the air temp sensor. That's, let's just look at this as one or the other. So this is coolant temp sensor. Most of the older vehicles, you have 1 wire going to ground. Now some of the newer ones, this goes back to the ECU also, does not go to ground. So on the 4X, it's going to be 2 wires coming out. One will go to this and the other one will go to, this other one, just in case. The 1X and the 2X have 2 wires coming out. Then we thought we could shortcut it because all the ones that we had seen thus far, the one side always went to ground. So we figured, why, we got a ground here. So we just run 1. But we're finding more and more of the newer ones that do not have the one side just going to ground. It actually goes back to the ECU. What are we accomplishing here? There is a chart. Let me see if it's in here, if I have to find a handout for you, where the coolant sensor, let me see if there's a handout here. The coolant sensor is a thermistor. In other words, it's a resistor, but it changes value, here's the handout, as the engine temperature changes. So the colder the engine, the higher the ohms of resistance across the sensor. As the engine gets warmer and warmer and warmer, the resistance values go down. The computer typically sends a 5-volt reference, but at a fixed amperage to this sensor. So as the resistance goes down, as the engine warms up, the sensor bleeds more and more of the 5-volt reference off the ground. The net result is that the high impedance sampling system in the ECU sees a lower and lower and lower voltage. Cold engine, high voltage. Hot engine, low voltage. Cold engine, lots and lots of resistance across our thermistor. Hot engine, it's almost like a short, very little resistance. So with that in mind, if we want to tell the computer that we have a hotter engine, then we want to reduce the resistance, right? A parallel circuit resistor will accomplish that. Means that we can take a resistor and just splice it across the 2 leads. Now the computer sees a hotter engine. It's that simple. Almost. When the engine's up to operating temperature, let's say this is a 480 ohm resistor. Whatever the resistance is in the thermistor, this is in parallel, so the total resistance will be less than either or. So we just told the computer that the engine's hotter. So that's great and all, but what happens the next morning when you try to fire the thing up cold? 480 ohm resistor, what does that say on your chart? Where are we at temperature-wise? We're already up to operating temperature as far as that chart goes, huh? So that doesn't work. Only when it's hot, right? So here's what we do with the optimizer. On the 4X, when you first turn the key on, this is going to be a 100K ohm resistor. On the 3X, it's a 10K ohm resistor. Approximately every 1.5 seconds to 2 seconds, it's going to drop in resistance, drop in resistance, drop in resistance, drop in resistance. About 5.5 minutes later, this will land at about 480 ohms. That gives the engine a chance to warm up. Same with the air temp circuit. Because if we have hot air coming into the engine, we have fewer oxygen molecules in any given cubic foot of air coming in, right? Fewer oxygen molecules means that we need less fuel to satisfy that oxygen and maintain that 14.71 air-fuel ratio the computer thinks we're after. So the computer sees hotter air coming in. Our optimizers say, hey, we're rich, back it off, lean it out. Oh yeah, well, that air is pretty hot. Yeah, you're right, I should lean it out. See that? Also, the hotter the engine, up to a point, the hotter the engine, the more the computer will lean it out. After you get to a certain point, though, the computer says, this is going to be a warranty issue if we don't do something like right now. So it goes into internal cooling mode. In other words, it just opens those injectors and just starts dumping fuel in there, hoping the latent evaporation process will cool the engine down from the inside out. So we don't want to get the engine too hot as far as the computer sees. You just want to get about 220 degrees. If you have a 195 thermostat in there and you take it up to like 215 to 220 Fahrenheit, you're in the ballpark. Some of the front-wheel drives have electric fans, and some of them will kick on at like 216 or 218. So you want to target this to where it's just under that cooling fan kicking on. If it's like a rear drive engine with no electric cooling fans, usually you can get it up 220, 222, and you're still safe. You're still a long ways away from internal cooling. The additional load of the fan running all the time will more than offset the little bit of additional fuel economy you'll get between 212 and 216. No fan, fan running all the time. Alternator running all the time. No alternator. So you want to keep it under the cooling fan threshold. And I'll show you how to adjust that later. You got the gist of what we're doing here? All right. The cooling sensor is a tuning method. So when you get into these kind of books and so forth, and it's talking about tuning, the cooling sensor will allow you to trim back the fuel with the optimizer without tripping codes, without ticking off the factory ECU.
This is the 4X.
This is the 1X, 2X, 3X, 4X. This is theory. This works on anything and everything. Telling the computer that the engine's at 215 to 220 is a pretty safe margin no matter what you're trying to accomplish. When it comes to the air charge temperature sensor, that is where we're going to retard ignition timing, because hotter air is more prone to detonate. So when the spark timing tables are programmed into the ECU, one of the offset values is air temp. So as the air temperature goes higher and higher and higher, the ignition timing gets more and more and more retarded. So you can go in here and alter the air temp signal and actually play with ignition timing. Isn't that nice to know? If you need more ignition advance, try putting less or putting more resistance in here. Give it a cooler signal on your scan gauge. If you want to try retarding the timing more, make the air hotter as far as the computer can see. Pretty ingenious, huh? You guys can do that. Even on coil on plug, DIS, doesn't matter. Now, of course, the older ones, you can always loosen the bolt and turn to the distributor. That's easy. But where you can't, here's how you affect your timing. Air charge temperature sensor. Now, you get so much and you trip a code. I know the GMs typically trip at about 243 or so, 243 degrees Fahrenheit. Worst case scenario, you don't want that air temp sensor reading more about 220 on the projected hottest day of the year that car is going to see. So if this were August 15th and it was 103 degrees outside, we could set that air temp sensor to read exactly 220 degrees and feel pretty confident that it ain't going to see much higher ever. But on a day like today, if we set it at 220 degrees as the winter wears on, it's fine. But come next spring, when the temperatures exceed where we're at now, he's going to start tripping codes. So now we have to think, all right, let's see here. It's 60 degrees outside. So, and we figured the hottest it's going to see is 105. So that's 45 degree swing. So 220 minus 45, that means we could probably set it at about 150 anyhow and be safe. You may not want it at 150. This gets into the tuning. Because remember, ACT, that's going to affect timing. So you just crank it up to the highest temperature you think is possible. Well, maybe you could actually benefit from a little bit more timing advance than you're giving the engine. So maybe reading cooler temperatures on the air temp sensor will actually deliver better power and better fuel economy. Are you guys following this?
Mm-hmm. Somewhat.
Yes, sir?
Put the air conditioning on, though.
The more resistance I add, the more I'm going to retard the timing?
All right.
Oh, it's gonna advance.
Okay, you see your chart here? Mm-hmm. Let's go back to a little basic lesson in electronics here. One K ohm resistor. If we take our ohm meter, put it across there, it's 1,000 ohms, 1 K ohms, right? Now, if I do this, and I put my ohm meter across here, I'm going to read a half K ohm, 500 ohms. When you go in parallel, you're going to split the resistance two ways. So 1,000 ohms and 1,000 ohms in parallel will give me 500 ohms. One side is going to be your actual sensor. The other side is going to be the optimizer circuit. Conversely, if I take my ohm meter across that, that is a series circuit, I will get 2,000 ohms reading. So that means that if coming out of my optimizer, I tap in here, and my temperature readings are too high, I got 253 degrees showing. I know that ain't right, no matter what time of year. I can go in, and I can put a resistor in line here, and that'll drop my scan gauge reading from 253 maybe down to 245 or 220, depending on the value of this resistor. Because this resistor is part of this resistor. I just drew this in, but this is actually inside the optimizer. This resistor is inside the optimizer. And it goes between this lead and ground, this lead and ground. So essentially, the resistance built in here would be just like putting one across here, but we're not doing that.